Hereby, I open this academic ceremony in which Raphael Phoebus Stolpe will defend the academic thesis, Embodied Neural Models, Closed-Loop Control of Neuro-Musculoskeletal Systems. May I invite you to present a summary of your study and the conclusions of your thesis.
Thank you, Pro-Rector. Esteemed members of the opposition, dear friends, colleagues, and family, welcome to this presentation titled Embodied Neural Models, Closed-Loop Control of Neuro-Musculoskeletal Systems. The motor control is a central function provided by the human brain, and people can experience significant reduction in quality of life when they experience impaired motor functions. So naturally, neuroscientists have always been interested in understanding the system better. One of the first things to note when looking at the human motor system is that it's hierarchically organized with several components fulfilling different functions. It starts with the motor cortex, providing high-level motor commands and sensory-motor integration. This then passes signals, which we call descending signals, denoted by the letter U here, towards the spinal cord, which performs the muscle coordination and integrates motor reflexes. The signal, however, is modified by output of the cerebellum, which performs an online adaptation of the motor commands. After the signals have passed through the spinal cord, the muscle fibers are activated and actuating the mechanical system that we call our body. The musculoskeletal system also fulfills several functions, such as joint actuation, but also mechanical compliance. This is a very, very rough description of the system that we look at. And when neuroscientists try to understand it better, what they do often is they build models, and those models need to be constrained. And there are certain ways to do that. One would be to enforce that the input to output relationship matches that of the actual system in the biology. Another way would be to enforce that the system fulfills a certain function. And the third one, which I'm going to talk about today, is called embodiment, and it means that we allow each of the components to dynamically interact with each other. To illustrate what I mean by that, I want to go over a quick example with you. So if we look at this figure of an upper limb, it has two joints, revolute joints, and they move along one dimension. What I mean with closed-loop control is we want to be able to prescribe a desired trajectory, here denoted in green, and then make sure that we can design a control input to this system that will enable the joint position, so the output of the system, to converge and then track the desired trajectory. So this is what the system would look like. We're looking at the forward simulation where we have the joint acceleration on the left. We integrate twice and we get to the joint position. In control theory, what we do is we measure the tracking errors between the actual and the desired, and we use that information in combination with the desired to inform our control input, in this case tau, so the torque, the forces applied at the joints. And when we do that, we see that the tracking errors can converge to zero, and we achieve trajectory tracking. If we look at the control input, it has a very interesting property, which is that provided we know the joint positions of the system, and we know exactly what the physical properties of the system are, so meaning the size and the mass distribution here, we can know exactly, we know that there's only one solution that would enable this trajectory tracking. So meaning we can know exactly what forces at the joint have produced this movement. And so this logic of the argument can be extended further, provided we know the torques that need to be provided, and we have an accurate enough muscle model, we can then figure out what are the muscle fiber activation signals looking like that have produced a certain movement. And by this is what I mean when I talk about model-based control supporting embodiment in neuroscience. So when we go further and looking at the muscle tendon complex model, it's built up in two segments. So we have the muscle fibers and the tendons. Each of those are modeled as elastic components. So you can imagine a rubber band. When you pull on it, it will produce a counter force. And so there's like a natural balance between the two. The muscle fibers, they also have a force generating component, which can be activated by the muscle fiber activation, shifting that balance. And then, of course, when you connect several muscle tendon complexes to one joint, there's also a balancing happening between the different muscle tendon complexes. And this already highlights the first problem that we encounter when we want to design control systems for this type of system, which is the overactuation property. So there are always more muscle tendon complexes acting on a given joint than there are joints in the body. And number two, muscles require to produce positive efforts, reflecting that they can only pull and never push. So in the control design, we have to take account for this. One solution that we came up with was to actually separate those different efforts into a positive and a negative component, which you can see here, where with the if you add the blue line and the red line together, they would amount to exactly the black line. But using the red line and the blue line, we have an easier time making sure that we when we transform from joint space to muscle space, which is higher dimensional, that we always have positive required muscle efforts. So if you go further in this development of the control system, we now look at two more tracking errors. So we're looking at the forces produced at the joints and the rate of change of the muscle fiber activation. And we could combine all of this information to inform our new control input, which in this case is the rate of change of the muscle fiber activation, denoted by the letter Q. As we use this as our control input and integrate the system forward, so we simulate it, we can see that first the actual torques converge to the desired, and then the joint position. And here you can also see an animated representation of this trajectory tracking. So here we can see on the left the normalized muscle tendon complex efforts that have enabled this tracking result, and on the right, the muscle fiber activation signals. And it's important to note that there's a non-trivial relationship from the desired trajectory that we tracked, which was a sinusoidal trajectory, to the muscle fiber activations that have enabled this trajectory tracking. So already here, control theory, nonlinear control is providing a great benefit. So now we want to extend the system further by incorporating the descending signal as our new control input. And this is what the system would look like then. So we'll measure the tracking error for the rate of change of the muscle fiber activation, as well as the rate of change for the motor neuron activation. We'll again try to use all of that information to inform our control input signal U, except that now we've actually used a little trick. So now we've replaced the muscle tendon complex model with a simpler model that is a predictor. We call it a predictor that predicts the output that the muscle tendon complexes provide, so the force that they generate, as a function of the muscle fiber activation. We account for that by adding the prediction error. Doing it in this way has several advantages. So number one, it greatly simplifies the derivation of the control signal, where at this stage already we're dealing with quite a lot of terms. But also we've noticed that as you differentiate the muscle tendon complex model, there are certain issues arising from it, namely that at the intersection between contraction and extension, there are some non-smooth regions that cause problems in the control design. And with this prediction, using a predictor, we can mitigate the effects of that to some extent. So now we'll use this newly designed control signal U as our new control input. One thing I wanted to highlight is the way we use this predictor is actually reminiscent to some degree of what the cerebellum does, which is this online modification of the control input. So using this system now, we can again verify that we can perform trajectory tracking in joint space. We have the separated joint efforts on the left. We can see again, so the predicted converges to the desired, and the actual converges to the predicted. So we achieve trajectory tracking. On the top right, we see the muscle fiber activation signal. On the bottom, we see the first transient of the control input, which is very, very fast. And on the right, we see the entire signal, and you can still see these sort of sharp, non-smooth regions, which come from this non-smooth features in the muscle tendon complex model. But they would be much greater if we hadn't used this predictor design. So now we've established that we have a control system, a closed loop system coming from the descending signal to the control output, to the system output, so theta, the joint space, in joint space. And now we want to use this framework where we have established that we can use it to embody or dynamically ground neural models, and we want to use that to study some of the models that we see in the literature. In particular, one model that I focused on was the 1A stretch reflex. So it's a system or model that measures the stretch of the muscle fibers and gets activated when there is an increase in the stretch. And it then will activate the motor neuron, which in turn will cause the muscle to contract again. So it's there to coordinate movement, but it's also there to protect the muscle from over extension, like an unnatural extension. And so we went to the literature. On the left, you can see this is what these models would look like. So you can see that what we found is that they are anchored around the parameters that we also use in the muscle tendon complex model. In particular, of interest was this reference length, which I'm going to come back to. We could see that the increase in activation as we increase the fiber length is not that steep. So we've designed a new model that we proposed that would reflect more this steep nature. And we predicted that in a scenario where we try to reach an unnatural configuration, we would see a much more pronounced response to it. So what we did is we regulated the system to be at 30 degrees for the elbow joint and 10 degrees for the shoulder joint. So it's a very natural configuration. We then asked it to extend the elbow joint below 0. So it's like overextension, something that humans can't really physically reach, actually. And so we wanted to look at what are the effects of the different models. And we could see that when we use the one from the literature versus no model, we don't really see much of an effect. As you can see, there's no real change in the joint position from the red line towards the blue line. When we use the one that we proposed, we saw that it does actually effectively prevent the system from going into this unnatural configuration. And we can also see that in the mechanical compliance, where mechanical compliance is sort of a counter force that rejects this movement that you request of it. It can be tuned, and also we think that it's believed that the spinal cord does a great deal in modulating it. We can see for the activation of the stretch reflex, we don't see much activation in the extensors, which is expected. And we do see mixed signals in the flexors. So here we have our proposed model in the continuous lines, and the dashed lines represent the one that we found in the literature. And we can see that the one in the literature remains fairly flat, whereas for ours, we see there are steep increases, but only for some muscles. So there's, for instance, the long bicep set that always is at fully activated.
Can I ask that you finish your presentation in 1 or 2 minutes, maybe?
Yes. And so the reason for that, we found, is that actually to simulate, we need some good balanced conditions in terms of muscle fiber length. And the way that we simulated this using only 7 muscle tendon complexes doesn't really support that. So there's no good solution to balance, to find like a muscle joint configuration that maps onto the muscle space. And therefore, the study that we've done cannot actually be conducted in this way, but this discovery was only really possible in the closed loop simulation. So in open loop, this would not really have come up. So therefore, we still think that it's a great tool to study neural models in the context of embodiment. With that, I finished my presentation.
Thank you very much. The opposition will be opened by Professor Dr. Ralf Peters, who is a professor in mathematical aspects of knowledge engineering at this university. Professor Peters.
Thank you, Mr. Prorector. And let me first of all congratulate you with a very nice presentation and a nice thesis that I really found interesting to read through. And also my congratulations to the supervisors. I have one burning question, and that is, what is wrong with your models in chapters 2, 3, 4, and 5? And I say this in view of your proposition number 9, of course, so maybe one of the paronyms could read out proposition 9.
Number 9. All models are wrong, but some are useful.
So, what is wrong about your models? Could you explain me?
Highly esteemed opponent, thank you for your compliments and your question. Yeah, I mean, so there are certain very concrete things wrong with the models, and then there's this natural fact that all models only capture certain things of the reality. So there's no 100% correct model. But in this particular studies, the muscle tendon complex model, as I highlighted, features these non-smooth regions, which is really unrealistic in the biological context.
Yeah, and that holds for all the models that you have there, because I think you build them up from chapter 2 up to chapter 5. And 3, 4, 5 are more or less similar, slightly differently written down than number 2, but yeah. But there's also the aspect of usefulness of the models. So what for these models do you find particularly useful?
I find that this closed-loop control framework to constrain all sorts of neural models, because this could actually also be extended further up the hierarchy even, right? If you provided you have a good model that you can use. And I find that it's actually a really useful tool to study. Of course, there are certain issues with it as well, like it's not perfect, but I think it's a good approach to ground neural models in the physical reality which they operate in as well in the biology.
Yeah, and where would you think that most of the usefulness resides? Is that in the, let's say, the neuronal, if that's a word, and the neural region, or do you think it has impact for the control strategies, and could it be used there? So where's most of the impact of your work?
Yeah, that's a good question. Yeah, so I do think that you could actually try and use this on patients, especially because you have this prediction-based control design. So it would, in my view, adapt really well to new parameters. Of course, you'd have to do certain updates, like you would want to use way more accurate muscle tendon complex models that are tailored to specific patients in this regard. But the structure of the control design, I do think it would work for that and could have an impact there as well. Of course, so for the neural studies, I do see that, once you go to the cortical structures and the cerebellum, it gets more difficult to find closed form equations, which is something you would need, right? Often you have neural networks that you use to model this. So that's a bit more difficult or more complicated to, it's not impossible, but complicated to do.
Yeah. And I was thinking about the control strategies that you have. You have an over-actuated system.
Right.
You have redundancy in the whole thing, and therefore also robustness. Mm-hmm. But are these concepts that you could use in engineering fields and other situations, or would it bring you a lot of complications? It's the kind of trade-off I'm looking for between parameter identifiability versus having all flexibility, and like in a neural network where you aim for that, where you have.
Yes. So if you had a tendon actuated robot, is the direction you're asking. I think that would actually have, that would be quite advantageous actually to use those robots, because they do actually have this property of mechanical compliance, right? So they would be much more subtle in their interaction with the environment, already built in physically into the system. And indeed, this over-actuation property does provide this robustness. So there, I think, yeah, that could actually be another application of this. Yes.
At the same time, it might come with a price, because I read somewhere in your thesis that the optimization is maybe costing a lot of time and effort, and you want to avoid these things. And wouldn't these over-parameterizations cause extra computations?
Yeah, I would say it depends a bit on the system that you're looking at. And
well, for your systems, you do have these multiple actuators, the muscle tendon pairs. So is that helping you or causing issues?
Can you repeat? Sorry.
So you have multiple tendon muscle pairs, and suppose you over-parameterize your system.
Right.
And then you have to make choices for all these pairs, and
Yes.
you do it in multiple ways.
Yes.
So does it complicate now, or does it help you?
I mean, yes, it's a bit more challenging to design a good control system for it. But at the end, I found that once you solve these issues, it works really well, actually. So that's...
Okay, I'll leave the discussion here.
Yeah.
Return the word to the pro-rector.
Thank you, Professor Peters. The opposition will be continued by Professor Dr. Auke IJspeert at the École Polytechnique Fédérale de Lausanne, and Professor IJspeert is joining us online. Professor. Unfortunately, we can't hear you. We have to check both on your side for mute and on our side.
All right, so sound check.
Yes, this is good, thank you. Continue.
Is it? Now it's better?
Yes, absolutely.
Yeah.
Please proceed.
Okay, super. Yeah. So first of all, dear Raphael, fantastic work. So it was really enjoyable to listen to you and to read your thesis. Also, to follow a bit your work in the Human Brain Project, of which we both participated. So congrats for a very nice achievement. My questions will be first about chapter 4, about this alternate stretch reflex model that you proposed. I think it's a model that makes sense from an engineering point of view, but how close do you think you are or not to the biological stretch reflex, which has been studied a lot? And would there be an experiment that you could make on humans to validate or not this alternate model that you propose?
Highly esteemed opponent, thank you for your compliments and your question. So yeah, I agree with you. This was done really from an engineering perspective. So I don't actually think that it's very good at reflecting the biological reality. However, we did find that it was still useful to think about what would a model actually need to provide. Of course, you could go. So I would. So measuring this system, these reflexes in an actual human, you can only really approximate for that, right? You could try to electrically measure the signals and then see, okay, what is the input-output relationship again, and then thereby trying to estimate good parameters for such a model.
Okay, yeah, thank you. Yeah. Then you have this hill-type muscle model in your model, which I think is a good model. It has all the non-linearities of muscles, like the force lengths and force velocity non-linearities, which are quite special to muscles. We don't have them in electric motors. So do you think these muscle non-linearities, are they intrinsically good and helpful, or are they just annoying features that you have to deal with?
I think they are both. So they are annoying to deal with, but indeed, like they have this, especially in open loop. I mean, they have this self-stabilizing property as well, and it's So they have caused great problems for me initially, but no, I think they are very very useful properties. especially also in the self-stabilization and the reactiveness of the systems.
Okay, yeah, thank you. Then you design your controllers and you kind of your spinal cord model as really a tracking controller that tracks joint angles. But in my experience, the spinal cord is more than that. So you have, of course, central pattern generators. You can create cyclic movements. You have muscle synergies to generate whole coordinated movement just by the spinal cord itself. And in that case, what the spinal cord receives as input is not a desired joint angle, but it's just maybe a desired posture or possibly a desired rhythm. Mm-hmm. So could your model be extended to do more than just trajectory following?
That's a very good question. I mean, that's one of the problems I already discovered with this model, which is that the control design actually kind of negates the effect of the spinal cord to some extent. So you have to look at certain tricks to still try and express the functions of the spinal cord. So one thing I did in chapter, I believe it's 4, to operate the spinal cord actually in the null space of the control signal, for it to express a little bit of an effect. So that's actually something, indeed, I completely agree. It doesn't fully cover the extent to which the spinal cord coordinates movement and all the capabilities it can do. Of course, then the way that you set this control design up, it's simply built to perform trajectory tracking. So you might want to look a little bit at, can you find ways for the spinal cord to inform the desired trajectory? Because also the sinusoidal trajectory is not really a natural trajectory that we find in biological movement. I mean, we can perform it, but it's not really like in a reaching movement, for instance, it's not really something we would naturally do as humans.
Okay, yeah, thank you. And maybe last question, if I may, would be about co-contraction, how to modulate co-contraction. So we, as humans, if we're on slippery terrain, we tend to co-contract. If we're learning, we co-contract more and then we relax. So there's a notion of rejecting perturbations, but also not having too much metabolic cost. So can you discuss a bit how to handle co-contraction? When is it useful to modulate it, and when should you just keep it constant?
Yeah, that's also a very interesting question. I mean, we looked at it really from the perspective of mechanical impedance. So we do recognize that the spinal cord likely optimizes several variables, energy expenditure, for instance, being one of them. And so we thought that it's actually sort of linked to mechanical impedance, and that if in situations where you have to counteract a force or prepare for movement, it could be useful to increase co-contraction, but of course mostly keep it at a minimal level that still enables reactiveness of the system, so not have the muscle tendon complexes hang entirely loose.
Okay, yeah, thank you. Thanks a lot. That's it on my side.
Thank you.
Thank you very much. The opposition will be continued by Dr. Rico Mukkel of this university. Dr. Mukkel.
Many thanks. I would also love to first take the opportunity to congratulate you on this very nice thesis, and of course also the supervisors actually for this excellent work. My first question, I would like to point actually to your page 3 actually of your thesis, where you make some very interesting statement. This is just to remind you quickly, you talk about and advertise a bit like the dynamic grounding framework that you use in your thesis. Also highlight, of course, as you described in your presentation, the possibilities to connect the physical and neural models in a closed loop structure. But then also make an interesting statement about the fact that this can also be used without actually knowing the prior function of some of these models.
Right.
And that you might actually be able with this framework to discover some functionality that is not prior known actually to the research field. So my question would be like, did you discover something like this as part of the work of your thesis, or do you have other examples actually to support this statement?
Highly esteemed opponent, thank you for your compliments and your question. I mean, yes. So I don't think I've discovered any other function that would not have previously been thought of for any components that I used in the model. But still, so encapsulating neural models in this closed loop setting, the models start to dynamically interact with each other, and that really can bring out functions that have maybe previously not been assigned to. So I still stand by that statement. But yeah, I'm very sorry. I don't think I have like a very
no worries.
Example.
For answering this. Because my follow-up question would indeed be like, so how would we design actually an experiment to discover something like this? So I'm with you actually, so I would also believe that this actually is possible.
Right.
I have a few works actually in mind, I think, where people indeed like show that. But I was wondering indeed like, what you would have in mind actually if you would design an experiment to discover such a functionality.
Yeah, so I think, thank you for your question. So I think what you would want to do is, so in the spinal cord, you have a lot of different pathways interacting with each other at the same time, right? And so based on the anatomical structure of it, people have assumed, and based on research, people have assumed that it provides certain functions. But I think in simulation, you can actually try and disentangle certain things. And one key property that I would want to look at is indeed still this mechanical impedance, or because the nature of the overactuated nature of the system implies that the spinal cord can address other parameters or other variables than just following a specific trajectory, right? So it is likely that it does, for instance, support optimization of mechanical impedance or energy optimization. And to that extent, I would then look at, okay, what neural circuits we find, for instance, in the spinal cord now, do actually have the biggest effect? Like, is it really the way we thought, or is there some other thing that we can observe in this closed loop simulation?
Okay, yeah, many thanks. Then maybe as a follow-up question actually of Professor Peters, who has very nicely pointed out the challenge actually of building good models. Your thesis of course highly depends and is founded actually on a majority of like different models, many of them actually of course from the scientific literature. I was wondering also in defense actually of all of these beautiful models that you're using, can you say a few words about like what makes the model actually a good model for you and how you actually have been maybe selecting one of these based on this criteria?
Yeah, so we've actually selected, for instance, the muscle tendon complex model based on what we found colleagues in the Human Brain Project were using as well. So we wanted to use the same models, but our colleagues were not really using them in the way that we were. So we had to differentiate the model much further than they had to. And so if you just look at, for instance, the rate of change of the muscle fiber length, it's still smooth, right? It's all fine. But once you go to the acceleration and further down, then you start having these problems. So this would be for sure a feature that I would look out for, that a model does have this smooth, because it's kind of stitched together based on experimental data, which it's a good model for that, but this property only really comes up in our work, right, or in my work, that it really becomes a problem. That's number one. Then there's also, I guess, the notion of, can we really just plug and play with it? So in the sense that we can take neural models that we find in the literature and just take it for face value, that they would connect well or work together with a muscle tendon complex model. To that I would say, no, that's not a given. We do have, of course, the properties that the input, so the output of the neural models is scaled between 0 and 1. The input of the muscle tendon complex model is also scaled between 0 and 1. But for instance, certain rates of change in the models might not really be aligned well to each other. That could be a problem, that also because they are just estimations from biological data. And for instance, I know that the neural models that we've worked with, as far as I know, they've been recorded in cats, not humans. So this is also a thing, yeah.
Okay, many thanks. If I may, one more question? Yes. Yeah. Short one. I would love to also refer actually to page 93, actually, your last statement actually on that page, that you have formulated actually in a very clever way. You said like once dynamical grounding actually can be applied to neural models. Of course, there are like many requirements that we have actually in order to make the statement actually come true. And a big challenge, of course, that we have is just the plasticity, of course, that we have in the human brain, where models often are quite difficult to achieve. Can you say one or two more words, just to be really brief, as in like what steps would be required and how would we potentially actually make a path so that your framework actually can be more broadly applied actually also to this more complex scenarios?
To specifically address plasticity.
Yes, please.
Yeah, I think so. I think the prediction-based control design already enables to capture some plasticity, but the models itself would have to be changed separately, I would say. So you can't really do it online in the simulation. You would have, you'd have to, I think, change individual models and address plasticity in that way. That's my...
Okay, many thanks. Yeah, I'm handing back. Thanks.
Thank you. The opposition will be continued by Dr. Isabel Bochner from the University of Tübingen, and Dr. Bochner will also be joining us online. Dr. Bochner.
Hello. Yeah. Thank you, and thank you, Raphael, first for your work, and congrats for this very nice achievement. It's awesome to see this finally wrapped up in this thesis and also in this presentation today. So the first question that I would be very much interested is in this third work that you're talking about, dynamical grounding. You basically evaluate neural models based on their functional performance if you embed them in a closed-loop neuromusculoskeletal simulation. Nevertheless, you also pose this question that this then obviously raises the trade-off between models that perform best in control terms, which might not be necessarily best for biological plausibility. So I'm really wondering how you would address this trade-off between functional adequacy and biological plausibility in your approach or in general. What would be your guidelines to tackle this trade-off?
Esteemed opponent, thank you for your compliments and your question. So how would I address this? So I think there are a number of things you can do to make this system more biologically plausible. So number one, looking at the biological plausibility of the different components that you use itself. But also, there are quite a lot of parameters in the control design that you can tune. We haven't looked at that explicitly, but there are, of course, you can make the control gains adaptive based on some biological findings that you could make. So one idea that we had would be to have some structure that would, in our mind, then reflect the role of the cerebellum to adapt some of the controlled gains to make the system converge, to behave differently in different scenarios, to converge faster to certain signals, or also to react differently to perturbation reactions. Perturbation rejections. Sorry. Yes.
Okay, thanks. Then maybe related to this, I'm also very much interested, if you're talking about parameters already, so also, especially in your first work, the approach that you presented, is there any chance that you could account for learning and improving a skill by adjusting your parameters? And if yes or if no, how would you include this? Maybe also considering, for example, co-contraction. If we think about having experiments where we have participants trying to learn a new skill, we see that over time co-contraction reduces. How would you include something like this in your model? Is this actually accountable for?
Yes, so those things are in all of the systems in different ways, but they're all parameterized, especially the co-contraction. So we have a co-contraction parameter in all parameters and all systems. So yeah, we would be able to tune that completely. So yeah, we could then look at the curve, like how does the co-contraction change, and we could map that onto the co-contraction parameters as well, and see if we can observe similar behavior to the biological data that we collected.
Okay, thanks. Yeah. And then maybe shifting also to your second work, where you proposed a predictor to map this input-output behavior of muscle tendon actuators. So if I understood correctly, you already embed the structure of your flexors and extensors and also biarticularity in your parameterization. Could you maybe elaborate how you could extend this approach further for a realistic use case where you not just have revolute joints in the shoulder and elbow joints, but more complex joints, and where also maybe the involved muscles are not always clearly separable in flexors and extensors? So is there any chance that you can make this applicable to more complex, more realistic systems as well?
Yeah, so I think here you could actually just try and see what happens first. So see if it would already work, because the prediction-based design is already quite capable of measuring or tracking the behavior in those contexts. But I do recognize, of course, that it would make the problem more complex, and you'd have to see to what extent it would still work well. But yeah.
Okay, and then maybe a last question. So you proposed this explicit closed-loop, closed-form formulation of this control structure. Could you maybe clarify a bit more how you can compare this to optimal control approaches, or maybe even reinforcement learning, and what additionally we gain from your insights based on your control structures compared to different approaches to controlling neuromusculoskeletal models?
Yes, so we've seen several approaches to this control problem in the literature. So the optimal control approaches that I'm aware of, they don't have this, they don't feature this strict model-based control, but they are a bit, maybe not easier to apply, but they would, for instance, I could imagine they translate better to the real biological systems. Other control approaches I've seen were using as well sliding mode control, and so in particular addressing the overactuation issue. I've seen a publication that used online optimization, which of course then is very, very slow. Also, to address that question, we do see, especially in these systems, in particular, also because of the problems with the muscle tendon complex model, quite some computational stiffness, causing the simulations at times to run fairly long, like at least longer than real time. And this would also be something where I see optimal control approaches in a better position. Yes.
Many thanks. Then yes. I think I'll hand over to the next opponent.
Thank you very much. Indeed, the opposition will be continued by Dr. Mario Zenden of this university. Dr. Zenden.
Yeah, thank you very much. Dear candidate, it was really a pleasure to read your thesis and see you presenting here today. Also to just see your entire trajectory, right? I've seen you from the masters, and to see you standing here is it's a very nice and it's a very big achievement, and I would like to congratulate you on this, and also of course your supervisory team. In terms of questions, I would actually like to stay where we just were a little bit with the biology and your controller. So in general, the controller that you have, and then also the predictor that you have, it's a very nice abstract mathematical formalization. So if you think of maybe Mars levels, maybe it's a little bit at the algorithmic level. So my question is, in the brain, how could this actually be realized? And what do you think the particular target system is that would realize this? I see it's a bit the cerebellum, but can you elaborate a bit more and also tell me how this would concretely be done and what kind of signals would be used?
Yeah, highly esteemed opponent. Thank you for your compliments and your question. It's a question that I've actually thought about many times before. Because you're absolutely right to point out that there's no, so the control design, I mean, it does follow the hierarchical structure of the motor system, but there's no one-to-one mapping on like a specific structure that we can do. We could say that the signals, this is a way to figure out what are the signals that we need to provide. And what we can also say is that we can be sure the brain has all of the information that we are using also available through the sensory systems, right? But is there really a structure in the brain that does exactly these types of computations? I would have quite some doubt about that. Like I think,
Okay, that's very
I think the brain integrates information differently. So this is actually something that we were thinking about in the future to take different components of the control design and replace them with a neural model, for instance. So for instance, we wouldn't then just take the joint position for granted because we don't actually, the human brain doesn't actually measure it, right? We can more like gauge it through proprioception or also the vision. So that there's somewhere in the brain is this information, but we would have to use more complex systems to then make that information available inside the brain. Yeah, I mean, somewhere there is this visual or like this sensory motor integration happening. So there's probably some unit in the brain that has all of this information available to it. But does it then do exactly these computations and also the, like with the, I don't know, I'm not sure, I can't say.
Okay, that's a very, very interesting answer that you're giving. So I like very much that there's not this one-to-one mapping, very interesting that you say maybe there's nowhere in the brain that does exactly this particular algorithmic implementation. Because my first thought was actually to go in the direction, I agree that probably it's not one-to-one mapping. I was wondering to what extent you would even support a one-to-many mapping, like a multiple realizability. Could several systems in the brain actually implement what you're doing? But the interesting direction you went is that maybe none of them do. But what would be then the alternative algorithms? Is there an algorithm that prominently from neuroscience might be something you swap in for yours?
I mean, I don't have one on the top of my head.
Just staying with the predictor.
Right.
Of course, there are differences, but to some extent, what I saw, they reminded me of things like predictive coding, right?
Right.
Where maybe something more akin to Bayesian filtering or Kalman filtering kind of algorithms might be implemented.
Yeah.
So could that be an alternative to what you're implementing? And I'm also interested in the other way around. So could what you propose be an alternative to those particular algorithms as instantiations of predictive coding?
Right. If you're staying with the cerebellum here, or like the prediction mechanism, I mean, there I would say that's sort of clear that that's happening. But this is where I would struggle. Like, I fail to see how this can be straightforwardly integrated in this closed loop control setting. Mm-hmm. So I don't think it's something like, I think you would need to change approach a little bit and try and use more the traditional like functional learning methods or like reinforcement learning to try and enforce that feature on the models.
So you would move more to more typically established cerebellar forward models?
Yeah.
Okay. Thank you very much. I have one other question that's a bit more about your control design and in opposition that you position it to reinforcement learning. I found it very interesting that you say that control designs that can leverage system knowledge will outperform reinforcement learning approaches that may not rely on this information. And my question is, how general is this statement? So first of all, what if reinforcement learning does incorporate this information? Is that possible, and to what extent would that leverage maybe the playing field? And then another question is there a scenario where reinforcement learning would come out ahead, and what does that depend on? Does that depend on the complexity of your task, or the available knowledge, the available system knowledge?
I think it would really come down to the available system knowledge, especially with nonlinear systems. At least in my experience with reinforcement learning, you struggle to learn the nuances. So you would really need to set it up in a very rigorous way, and probably also need a lot of training to really be able to capture this. This being said, so of course it's easier to say, like, so for instance, if you were looking at a task like in-hand object manipulation, it's in my opinion more complicated to design in this control theory way. But I would still think if you could do it, then it would outperform most likely in accuracy the reinforcement learning approach.
If you could do it. Where's the moment that you know you can do it?
I mean, so you just need. I mean, I haven't done it, but you need to really have a good model of the hand and all the different muscles. It's not impossible, but it's a little bit challenging.
Okay, I agree.
Yeah.
Thank you very much.
Yes.
Thank you, Dr. Zenden. The opposition will be continued by Dr. Tonio Weidler, who is a postdoctoral researcher at this university. Dr. Weidler.
Thank you, Pro-Rector. First of all, I would also like to congratulate you on this amazing thesis, also your supervisory team. It was really nice to read something that so clearly builds on top of each other, like every chapter is improved, or like points out what is missing, and then in the next chapter you improve this. This was really beautiful. For my questions, I would like to, because the opportunity has been given by you already, immediately connect for no particular reason to in-hand object manipulation. So, as you know, I work with a very different kind of models, which are more on the cortical level, and try then to biologically plausible model the way that we maybe generate these signals that would control a motor plant like the hand in order to fulfill some function. How do you think can we integrate your modeling approach that is more downstream and the modeling approach of a neuroconnectionist way in order to mutually benefit, or at least benefit the kind of models that I'm building?
Esteemed opponent, thank you for your compliments and your question. So I think I alluded to it a bit already earlier. Is that in theory, if you have a closed form expression for, like you say, higher, more abstract neural models, there's nothing really stopping you from doing that, at least in theory. But the connectionist approach, like if you really write out all the equations, then it becomes very, very long, very tedious to do. Maybe you could automate some of that, but you would then. So if you really use the connectionist approach, you would then still, in my opinion, so you could. Well, actually, you could probably build it up hierarchically and then work your way forward. Where if you always know what the output needs to look like exactly, you could perhaps parameterize such models consecutively in such a way that they reflect reality. And you could then, of course, I mean, you could use really biologically plausible, like column-based cortical models as well. And perhaps that would yield some really nice results.
Maybe then, so like what I understand is that you allude more to like how could your approach be used then in cortical models, right? Or like where we really have like a connectionist approach. But maybe let's say like we just stay one model type, the other model type, and we somehow link them together, right? So I take your model and I just generate the kind of trajectories that the more cognitive model decides are necessary in order to fulfill some function. Do you see challenges there? Can we just do this? And how would this improve the plausibility of the cortical model?
Yeah, I mean, so yeah, provided so you could actually, I mean, you could just take a neural model and learn the input that the control system has provided, and then you just you can just run it in, I like to call it a broken closed loop, or you still have some feedback, right? But you wouldn't have to have this path where you compute the control input. You could just use the neural network. And I would expect it to work a little less well, like the tracking would be a little less accurate and might be a little bit wobbly. But I would expect it to be learnable, yes. So then, yeah, you could make this connection actually, yeah. So it could be like a crutch, if you will, for models like yours to, yeah.
Okay, thank you. Can I, for my next question, ask one of the paronyms to read out proposition 8?
What I cannot create, I cannot understand.
So this is, of course, a very famous quote. And I would like to you to allude more towards how you think this applies to your work. What have you created? What have you understood? And to what regard do you think your models are mechanistic explanations? And to what are they just replicating function?
Yeah, so like I said, I do think that this is a very viable way of figuring out what are the actual signals that are being passed on through the hierarchy in the motor system. I don't think that the control law itself, like I said, I guess there's no structure in the brain that I would say, okay, this is where it's happening. But still, I do find this approach really, really useful to try and build things from the ground up. It's actually taught me a lot of things, mostly actually about the innate properties of muscle tendon complexes. And for instance, one I could perhaps highlight was, and I spent quite a lot of time on this, that maybe this kind of answers your question from earlier. So for instance, there is literature on the way these muscle tendon complex models are parameterized. You have either very long tendons compared to short muscle fibers, or longer muscle fibers to shorter tendons. And this already determines the role of the muscle, if you will. So it's really the way it functionally interacts. If you have like a longer tendon, it tends to be a lot less stiff. And what was the question? So this I really only discovered by using this closed loop control framework, because it started to become a problem, and I was figuring out what do I want these parameters to look like, and yeah.
Okay, thank you. And what if you think you would transport this proposition to the entire brain, right? Mm-hmm. And you would want to understand the entire brain. Do you think this actually applies? Because it is, as you also describe in your thesis, so complex that we could never, by hand, really understand what we are doing when we are setting different connectivity strengths and so on.
Right, yeah.
So we would rely on some optimization to do this.
Yeah.
Do we then really understand anything? Or do we just replace the thing that we are looking at?
Yeah, that's a good question. I would still say that this approach of embodiment does, in theory, the theory holds, like it does really provide you, enable you to...
The candidate is allowed to briefly finish the question.
Okay. So in theory, the approach of embodiment really allows you to understand the whole brain. Like there's, in my mind, no argument against it. And it's clear that the brain is situated in the body, and it's a huge constraint, like it forms the way the brain works.
Thank you, and thank you. Phoebus Raphael Stolpe, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. I request that you and your company await the results of our deliberations and our return in this room. Phoebus Raphael Stolpe. The degree committee here present has assessed the quality of your thesis and your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Goebel is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
Please all rise.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent and responsible?
Yes, I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Phoebus Raphael Stolpe, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with the degree certificate signed by the rector, the secretary, and the other members of the committee and affixed with the official seal of the university. Here it is.
Please be seated.
So, Herr Dr. Stolpe, I learned only by the preparation for today that you have the name Phoebus in front of it. You not use it, right? It's the first name in the document.
Yeah.
But you decided, your parents decided to use...
Yeah, they've decided to use Raphael, yes.
Okay. Dr. Phoebus Raphael Stolpe. Yeah, and I want to also extend my congratulations to the family. I know most of your family, if not all, are German, so herzlichen Glückwunsch, Sie können stolz auf ihn sein. Du hast deine Arbeit deinen Eltern gewidmet, to my parents, right? Und das ist auch, worauf man stolz sein kann. So I continue in English, and I want to say it was a great defense. It was Raphael how I know him. Very honest, very clear to the point, no nonsense, right? Very good. I was very proud of you. And I also want to thank a person who's not here, Yannick Morel. There were ups and downs, but you know, Yannick has had all the knowledge, was the guy who supervised you daily and guided you through the topics. So I really want to thank him here also for his contribution. And I want to also thank all Corona members. Thanks a lot for your good questions, also online. Thanks so much. I think that challenged you enough to show that you know something. You know. And usually at this day, one looks back. How did it all start? And in my case, I did not know you before you started in the HPP, but we looked for another PhD student who worked with Yannick next to Michael Zechmeier, which you know very well, on neurobotics, on kind of different problems within neurobotics. And actually, when we looked around, we got an email from one of our opponents, from Mario. Mario sent an email on 17th September, I checked this yesterday, and actually said, I know a guy which you should consider, Raphael Stolpe. I know him from a master thesis in systems biology, where you worked on deep learning networks, and actually on dynamical system perspectives, right? And he would probably fit well, and maybe he's interested. So then we, especially Yannick, of course, talked to you, and then you decided to go for it, which was great for us, of course. And yeah, then months later, so in October, you already had a contract, and we started. And of course, I realized this guy must be smarter. Also, when I see your thesis, which I'm not, of course, an expert in the work you do, I'm just admire what you do, but it's full of mass. I'm quite impressed. It looks cool, right? This is really, really nice, I have to say. And yeah, and this especially in the knowledge that you studied biochemistry, right, in Tübingen, and then, of course, in Maastricht, master in systems biology. So these are not, there's mass involved, but it's not that heavy like control theory. So therefore, congratulations to dig into that. And I heard that you are such an enthusiastic guy who deeply goes into things. And that, I think, was probably crucial for your success in this thesis. Yeah, and I saw you actually, or say it that way, it started, of course, still in the high time of COVID when you began, in end of 2020, so October 2020. And that was not a nice time. We had no person meetings, so I didn't see you, maybe sometimes on Zoom, next to many other people in the small fields of a big Zoom, right? And yeah, it was great to see how you teamed up, not only with Michael, with many other people around you. Some are here, many are here. So that was great that you really connected to people. One of your opponents, Tonio, I know that you had also a very special relationship, and the discussion showed it. You were almost back in lab mode. It was great to see. And so that was good that you all together survived this hard time, right? But I remember very well when we then finally had the first in-person meetings, and I decided to do in-person meeting of the project, Work Package 3 in the Human Brain Project, where you were appointed in. And we did it in Amsterdam, and that was really great. I saw people, you also, and many others, discussing a lot, being almost euphoric that we have these meetings again, you know, that we see in person and exchange. And it was really great to see, and I think that was also the time where we talked for the first time a bit longer. That was really great to have this meeting. You also, I think in the same year, moved to Lausanne, actually to one of our opponents, Professor Eike Ausbert, and actually there you did an internship in such a famous lab. I think that was quite something for you, right? You learned a lot. And how long were you there, actually?
Actually, only 2 weeks.
2 weeks.
But was a great
but still,
time. Yeah.
2 weeks in that lab is really cool.
Yeah,
very good. Yeah. And yeah, let me see what I else have on the list for you. Actually, when I just the other day followed some internet stuff, I found this thing, maybe you saw, and I thought about you. I found this story about Neo. Do you know? Did you follow that? There's this new robot, Neo, which cleans your house dish and does everything. And I was so impressed and thought, oh, I should tell Raphael during the defense, everything you try to do is already solved. Right? And then there came the journalist to this company, and she figured out this whole Neo thing was fake. This guy was remote controlled. A guy had glasses, saw what the robot saw, and moved the arms. This was not self-movement. He didn't solve any control problems, right? So I'm not saying they did not do any progress, but not the progress they pretended to. So I'm just to say it because your work is still super important and needed in the future, I'm absolutely sure. Because understanding embodied cognition, which was a topic of our HPP, is a damn difficult thing. You need so much world knowledge, so much how the messy world can interact with a moving agent, with a body, that is not so easy to solve than some people now try to pretend people and sell already things. Yeah, how did you relax? I learned that you did some long bike rides, also with Vojta. I think from Maastricht all the way to Bavaria, also until Austria. Is that true?
No, that's I don't know how you got that. I did a bike tour In the region, yes.
Yes.
I did a long bike tour there. Actually, already before I started the PhD, that was like a
Oh,
2 week
good.
long.
Yeah.
But yeah, but with Voitasto, we did some really nice, like we went to Cologne, for instance.
Oh, yeah, yes.
We did some very nice bike tours, yes.
And is it true, maybe my sources are not fully correct, but you also did some trained for a marathon? Did you do a marathon?
Yes, I did actually.
With this guy?
No, with him.
this guy?
Yes.
Okay. Yeah. Too many students. But I heard some rumors and tried to cook it together. Yeah. So I want to also convey deep congratulations from Judith, who helped a lot, especially towards the end of your PhD. And Judith gave me a certain text, which I want to read on her behalf to you. She asked me to do that. And it is quite poetic, and I want to read it to you. Judith. Raphael, you've always been a true team player, radiating positive energy. I still, Judith, remember how in the Systems Biology Neuroscience course, you eagerly volunteered to participate in a neurofeedback fMRI experiment. That's something I developed, fine. So your classmates could see through your mind control, closed loop motor control in action. And motor control stayed on your mind, eventually taking shape and culminating in your elegant embodied neuromotor models. Whether running races, cycling, bouldering, or playing paddle, you truly embody dynamic motor control. And with the cognitive control and stamina, you showed all the way through to the finish line. You've become an inspiring, all-round role model. Congratulations, Dr. Stolpe.
Thank you.
Finally, I want to say that I'm really very proud that you made it. I know there were ups and downs, but you stand here and defend it super well. And I also wish you all the best for the future. Actually, now I heard from Mario, can tell you from whom I heard it, that you have this wonderful plan to build your own startup.
Yes.
And actually to use machine learning to discover new proteins and protein configuration. And this will bring you back to your roots in biology, which is interesting. And I wish you for that very exciting plan all the best for the future.
Thank you.
Congratulations, Raphael, and enjoy your special day.
Thank you very much.
Dear Dr. Stolpe, also on behalf of Maastricht University, I congratulate you with the degree that you have acquired. I also want to extend those felicitations to your family and friends. And I want to especially once again thank all the opponents, particularly also the ones coming from outside. Thank you very much. With that, I close this academic ceremony, and I will only make a few housekeeping remarks. It will be in what we call the museum, which is that part over there of the large hallway where the stairs are. I would ask all the family and friends to already proceed there. We will stay here, the opponents and the doctors and the paranymphs, to make a picture. We will make another one on the stairs and then join you later. And with the one